Hello everybody, it's Monday, and today we're going to be talking about the periodic table. It's been 100 years since Mendeleev created it, 150 years that is, and I'll be talking about that real soon. Okay, I'm back over in Maui again here. It's 10 a.m. here, and in London it must be 10 hours after that, 20 hours. So the periodic table, you've all seen it. It's copyrighted, and I'm sorry I can't show it to you, the old standard periodic table. Since it's copyrighted, I prefer just to let you look it up in your approved sources. And all I'm going to be showing you today really is original work that I've done on the periodic table. Now, as a general comment, the standard periodic table has the lanthanide series removed and the actinide series block of elements removed from the table and placed in two little blocks down at the bottom. Let's see, I put them back into that so that the nuclear structure can be compared. Now, on the standard table, as you've seen, there's 7 rows. These are the periods, and there's a bunch of columns. These are the groups. Let's see, there's 4, 6. Looks like 20 columns. I'll just go count them again from left to right here. I have it on my screen. Let's see, potassium is 19, krypton's 36, so there's 18 from left to right that they've taken out a bunch at the bottom, 14. So in the lanthanide series, they have taken out 14, leaving 18. So the total width is 32. Now, I brought up the new periodic table onto your screen there, and I'm going to be zooming in on sections of this, but in this you can see the 7 rows. So at the top is hydrogen, top left, and then lithium and sodium, and down, 7 rows. These are the 7 periods. Now, period 2 is lithium and beryllium, boron, and those things. And then when you get down to lanthanum, that is in the 6th row. You see they've taken out everything from cerium over to lutetium and put it in its own block at the bottom. Now I put this all back in on this. I know it's blurred for you though, so you can't see it very well. And in a minute I'm going to zoom in on this and show you a better picture of that. For example, on this section here, you can see there is the iron labeled in large letters. This is the nuclear structure, and you can see at the top row is the period number 2 with carbon in it, and then 3, silicon, 4, titanium, and 5, period 5, is zirconium. And that's in the group 4 in this picture, because I've straightened out the entire table, so it's 32 wide now. Like if we go back to look at the overall periodic table, the width at the bottom is 32 elements, and then so that's period 7 is 32, period 6 is 32, and let's see, but period 5 is not. That's only 18. Period 4 is 18 with iron in it. So let's look again at iron in period 4. And I want to explain this new structure I'm showing here. This is the static nucleus theory, where protons and neutrons are treated as spheres. The sphere stacking forms a lattice with a cubic lattice at the center, and each face of the cube is then covered with a different type of lattice. And as seen from the exterior of the element, it's a hexagonal close pack. So the outside of iron is protected by the structure of the hexagonal close pack, but the center of it is a simple cubic structure. So this is a major breakthrough that I've been telling people about. And in this you can see the cube has 3 layers in iron. Now I'm going to show you with the camera what some of these things look like. Now here we can see the iron nucleus model, and I'm going to rotate it around for you a bit here. Now this has the same structure as you just saw in the periodic table, that there are small pyramids on top of a cube. So here you can see the cube. There's white protons in this in a square shape, and it's a 3-layer cube. And then on top of it is a small pyramid with 5 protons and neutrons, where the neutrons are in brown. Now with the little pyramid going on there, it's like lithium covering up one part of the cube to form iron. And I believe this is why lithium is rare in the sun, but iron is common in the sun, because each nucleus of iron consumes 6 lithium nuclei. So if you turn it around this way, you can see the ring of protons for iron. And a long time ago people asked, why is iron magnetic? And now I've discovered it's because the nucleus has 2 coaxial rings of protons. Now you can see that over here in this other model, which I'm going to show you. And the proof that this is persuasive and this is the correct theory of nuclear structure is enforced by the fact that iron has these 2 coaxial rings of protons in blue here, and the white neutrons in this model. And notice that it's lined up like a little circle. Now, if you just add one more proton, you get cobalt, and one more, and you get nickel. And that one goes over here on this central portion. Now, if you add one more proton, it ruins the ring, because that gets added on to the central part, and it causes a short circuit between this ring and the axis on the center here. That's why copper is non-ferrous, and iron and nickel are ferromagnetic. But it also is well known that the element gadolinium is ferromagnetic, and yet it's far heavier. There, you can see how much bigger gadolinium model is than the iron model. Let's see. Kind of side-by-side comparison. And really the gadolinium is shaped much like iron, with the 2 coaxial rings and an axis with these blue protons, green protons in it. So this is part of the evidence showing that the static nucleus theory is correct. Because then if you start adding more protons to gadolinium, it becomes much weaker and becomes called paramagnetic for the heavier element beyond gadolinium. It has two coaxial rings of protons, therefore it is ferromagnetic. There's iron, has two coaxial rings of protons, so it's ferromagnetic. Now, you can see the little pyramids there and in the diagram that I'm about to show you. So I'm back to the silhouette of nuclear structure. On the top right, you can see there the iron silhouette with the cube at the center, 3 layers in red. Now the red signifies baryons. That's protons and neutrons. And all the black circles are also baryons, protons and neutrons. And they're all treated about the same for the foundation elements. There are 18 foundation elements that have a simple structure of a cube covered by 6 pyramids. Now the incremental elements, like manganese, have these blue circles for the protons. So that is basically argon is a foundation element, and then protons get added on top of argon to form manganese, along with neutrons added on top. So in this periodic table which I'm promoting, which I'm not copywriting, that you are welcome to get, in this one, all baryons are treated the same to make the structure of the nucleus for the foundation elements, and then for the 90 or so incremental elements, then the protons are shown on this periodic table. All right, so I'm going to go back to a different photograph now, which shows a different part of the periodic table. So this is now lower down in period 7 at the bottom, uranium, and period 6, like cerium, up there. And you can see that they have silhouettes that are like crystals. It's a lattice called the face-armored cubic, and I've straightened out all of the lanthanide series here and the actinide series. So since this is now in order, you can see whether the promethium is directly below technetium, as you can see on the overall diagram. The periodic table of nuclear structure. I know it's blurry for you at this scale, but in the middle you can see the technetium is right above promethium. You can get a copy of this that's much clearer than this, and you can get that at my website, which is pyramidalcube.blogspot.com. And there you can just download the new periodic table of nuclear structure. But what I want to do now is go to some photographs of different things. For example, my text. There, you can see my plan is the periodic table after 150 years. Would Dmitri Mendeleev recognize it with this lanthanide block shuffled aside? Well, maybe. After all, the periodic table is made up for chemists. They want to have each group have similar chemical properties. Like lithium and sodium are in the same group, the vertical column. And then there's a lot of confusion, though, about the lanthanide elements and their chemistry and the actinides as to whether they are hybrid orbitals, and whether there's relativistic effects and things. And now I want to zoom in on this other thing I have here. Oh, there it is. Nihonium. All protons treated the same as neutrons. All are equal in the eyes of fusion. The placement of protons is guided by electron pairing. That there's an exclusion going on during fusion. And that is keeping the protons lined up in protons in lines of protons, not shown here. But I can show you different sections of the periodic table very soon now. I'll try to bring that up. All right. Oh, yeah, that's right. I can zoom in on this. Here I have a picture of gold, gadolinium, and iron, which I can zoom in on a little as close as I want today. So in this picture, it's the periodic table of nuclear structure, but for those three elements, I've labeled the protons in gold, in yellow. So we're going to zoom in on first iron, which I've already showed you the model. Okay, so you can see it looks like that model with a ring of protons. Loop 1 of protons on the right, loop 2 on the left. And then I can also show you at this high magnification, show you what gold looks like. And platinum and gold are like this. And tungsten, they all have a similar silhouette. And tungsten is the foundation element for gold. And on the model of gold, you can see there protons line up with protons. And inside the cube, protons repel protons. And outside the cube, protons line up into lines of protons. Now, of course, gold is nice for things, but platinum is better for catalyst. And it's shaped almost the same as gold. It's just that it's one less proton. All right, now gadolinium. Here is the proton markings on the silhouette of gadolinium. See how it looks exactly like iron. That's why it's ferromagnetic. Now, I have a conjecture concerning these elements that are close to gadolinium. Now, let me zoom in a little closer here so you can see how. Gadolinium's up here, element 64 on the top left, and next to it is terbium, and then a smaller element is europium. And this terbium is paramagnetic strongly, and it's right next to gadolinium. Now, dysprosium is also next to terbium here, and it is strongly paramagnetic. Now, my conjecture is that it's really weakly ferromagnetic, and that it can be made into a permanent magnet with a very weak strength. And then gadolinium, of course, can be made into a bar magnet with a medium strength. And the iron is a very strong magnet. Like when you buy the neodymium magnet, it's 83% iron. And the rest is a little bit of boron and neodymium. So this periodic table then is read as follows. There's 18 foundation elements. All of the noble gases are foundation elements, so you don't see any blue on them here. These are all just protons and neutrons treated equally, making a face-armored cubic lattice. And as you get to the heavier gases, they, like krypton, it also is a foundation element, and it then can have one proton added to it to become a different element over here. Rubidium. Yeah, if you just take krypton, foundation element, and you add on one proton in blue here, you get rubidium. And when you get your copy of the periodic table at home, you can look at this. It looks just like what I'm showing you. And then you can see strontium has 2 blue protons on top of the noble gas. Yttrium has 3, these blue circles. Then you go into a whole new class, zirconium, a whole new foundation element. Now it has a cube 3 in it, and then several incremental elements follow it. Neodymium and molybdenum, for example, are built upon the foundation of zirconium. So they have 1 proton in blue and then 2. And technetium is not worth mentioning. I can't even find any. So zirconium continues to be the foundation for all these other elements, ruthenium, rhodium, palladium, silver. So there's silver. Now, right below this is the lanthanide series. And it's just like this zirconium type of setup here. Oh, that's a good picture. Where the zirconium here is at the beginning of, it's a foundation element for a bunch of other elements that are incremental on top of that. And then below it is cerium, which is also a foundation element in the same position in the periodic table. And that is not designed by me. It's more of a discovery that I made about the structure of all these elements here. So cerium is a cube 3 element, and zirconium is a cube 3 element. They have simple pyramids armoring each of the 6 faces. And then as you go over farther, you get new foundation elements. There's hafnium, and tantalum is a small group of just 2 elements based on hafnium plus 1 proton becomes tantalum. Beyond that is tungsten. I'll zoom in on that closer. Oh yeah, there's tungsten next to the gold one. And you see it's different than hafnium. Hafnium has a cube 3, and then the pyramid is dilated down to 3-layer dilation. Whereas tungsten has a bigger pyramid on top with 6 layers, and then a bigger dilator underneath it where it fits onto the cube 3, and it fits in to this very tightly as sphere stacking goes, as if you had cannonballs and you're trying to make a pile. That's what it looks like. And so, for example, if I go to the camera picture here, I can look over here and see one of the things I'm talking about. There's the Pyramid 4 model. Tungsten has a Pyramid 6, and this is the Pyramid 4. You see it's like just a stack of cannonballs with a square base. Technically, you could call the overall molecule, the nucleus, as a tetrahexahedron. And some of the light elements have a cube 2 at the center. And you see that the cube 2 has 8 neutrons here in brown, 8 protons and neutrons. There's 6 neutrons in brown and 2 protons in white. And this core of the light elements having 2 protons is the reason why chemists have 2 electrons in the s orbital. There's a direct connection between the nucleus and the electron orbitals, and this is consistent all the way up to manganese. He's within the cube 2. Beyond that, you get the cube 3. So once you get up to iron, it's different. You don't have 2 protons in the center matching 2 electrons in the s shell. You have 8 protons in the center of iron. I'm sure that couples not to 2 s electrons, but 8 electrons in the lowest shell. I think they call them transition elements because they don't understand that there's a cube of 8 in the middle of iron. They expect chemistry to continue using 2 in the s orbital, even though it doesn't have just the simple 2 protons in the center, like carbon. Then things that are lighter than carbon are, for example, boron, or this one, beryllium. Yeah, beryllium has 4 protons and 5 neutrons in brown. And a law I'm advocating here is that protons tend to form lines of protons in the nucleus. Except inside the cube, the protons tend to repel protons, as you would expect from electrostatics. Now that I have shown that the cubic shape has gaps in it that are large and they're vulnerable, I'm proposing the strong nuclear force is gravity. And these models can use then hydrodynamic simulations, so that any Blender files that I have, for example, can be used to start the hydrodynamic simulations. Really, they just need basically the boundary conditions. So I'm going to open up one of these Blender files, and oh yeah, there's promethium. Oh yeah, nice camera work there. Yeah, that's great. So anyway, I'm going to be winding up now in my half-hour presentation for today. Thank you very much for looking into some of the details, and you can get this periodic table at one of my websites, for example, at impuremath.wordpress.com. Thank you. My name is Alan Folmsby, and I'm going to be signing off now. Thank you very much.